Hey everyone, welcome to another session of CeerazzleDazzle Physics. In today's session, guys, we're going to be doing a full GCSE Physics past paper, and this will be a full walkthrough, guys. So today we're doing AQA GCSE Physics Higher Tier Paper 1 2021. Make sure you have done the paper yourself beforehand before watching me do it. There's no point watching me do it, you have to do the work. But obviously it helps to watch someone actually walk you through the entire paper. Okay, and before we start, the first thing I'd like to talk about is going to be timings. So we have 1 hour and 45 minutes, that equates to 105 minutes over here, and it's 100 marks available, so 100 marks are available here. Just keep that in your mind, that is roughly a minute a mark to be able to do this paper. Okay, so let's start. I'll crack on with question 1. Question 1, figure 1 shows an electric car being recharged. The charging station applies a direct potential difference across the battery of a car. What does direct potential difference mean? Hopefully we can remember that in GCSE Physics we know that the potential difference can flow in two different ways. It could be direct, so look, I've got a voltage time graph over here. It could be direct like this. This one's going to be direct, or we know that it could be alternating, going up and down. So this one's going to be AC, alternating current. So therefore the word direct potential difference, what they're really asking you is that we know that for direct potential difference that the potential difference is always in one direction. So that is going to be the answer they're looking for. The potential difference is always in one direction, here. That's going to be the start. Okay, easy stuff here. Right, and the examiners also accept, I'm just looking at the mark scheme, they also accept that the polarity of the battery is not reversed, because the polarity of the battery does matter. So the polarity of the battery is unchanged. That's also acceptable. So polarity of battery is unchanged. Here. Polarity of the battery is unchanged here. Easy stuff. Okay, now scrolling down. Question 1.2. Which equation links energy, transferred power, and time? Hopefully we can remember that energy is equal to power times by time over here. And therefore it's going to be energy is equal to power times by time over here. Easy stuff. Next one, 1.3. The battery in an electric car can store 162 million joules of energy. The charging station has a power output of 7,200 watts. What's the time taken to fully recharge the battery? Well, we can reuse the equation we looked at above and just rearrange it. Energy is equal to power times by time. And the energy is 162,000,000 is equal to 7,200 times by the time. Yes, we don't know what the time is. Rearranging that with some bit of algebra, T is equal to 162,000,000 over there, divided by 7,200 in a calculator. 162,123,123 divided by 7,200. I'm getting the value of in seconds, 22500 seconds. Yes, and that's correct with the mark scheme, 22500 seconds. Okay, scrolling down for the next one. Okay, which equation links current, potential difference, and the resistance R? Hopefully we can remember that. V is equal to I times by R, so this is the correct answer here. The potential difference across the battery, 480 volts, is 480 volts. There is a current of 15 amps. Calculate the resistance. This is relatively easy. Voltage is equal to current times by the resistance. Then we're just plugging it in over here. 480 is equal to 15 amps times by R. Therefore, R is equal to 480 divided by 15, everyone. 480 divided by 15. I'm going to get 32 ohms, everyone. So 32 is our answer. And yes, it goes into here, 32 ohms. Easy stuff. Right, scrolling down for the next bit now. Different charging systems use different electrical currents. Charging system A has a current of 13 amps. Charging system B has a current of 26 amps. So you've got two systems here. One can charge at 13 amps, one can be at 26 amps. The potential difference of each one of them is 230 volts. How does the time taken to recharge a battery using charging system A compare with the time taken using charging system B? Well, the key thing is about the current. If you've forgotten what current is the rate of flow of charge. So the higher the current, the quicker it will charge. So we know that B, because it has a higher current, it would take a shorter time. And the 13 amps will be a longer time over here. So what we're looking for is the time taken for system A will be double the time of system B. So think about this. System B has double the current of A, so therefore it will be done in half the time. So this is the reason why we've taken the time taken using system A is double the time taken of system B. Easy stuff. Okay, scrolling down. The energy from the sun is released by nuclear fusion. Complete the sentences. Nuclear fusion is a joining together of, it's not particles, it's nuclei. Yes, nuclei together. During nuclear fusion, the total mass of the particles is what? Well, think about this, and hopefully you can remember in nuclear fusion that you have the nuclei and they get forced together and they become a new nucleus over here. So obviously they get fused together over here, and obviously there's some energy released here. There's some energy released. So this is a before stage. I'm just going to just very simply, this is a before, and then afterwards this is an after stage here. They fuse together. This is nuclear fusion. Energy is released here. But the mass of it beforehand will be greater than the mass of it afterwards. So there is going to be a mass loss. So therefore, during nuclear fusion, the total mass of the particles will decrease. Because at the start, these two have masses, and afterwards they fuse. Yes, this has a mass, but it will be less than beforehand. Because some of the mass has been converted into energy. Hence why during nuclear fusion, the total mass of the particles decrease. Because some of the mass has been converted into energy. That's the reason why. Okay, now next one. Nuclear fusion of deuterium is difficult to achieve on Earth because of the high temperature needed. Electricity is used to increase the temperature of 4 grams of deuterium by 50 million degrees Celsius. The specific heat capacity of deuterium is 5,200 joules per kilogram degrees Celsius. Calculate the energy needed to increase the temperature of deuterium by 50 million degrees Celsius. Use the physics equation. So energy is equal to what? What are we going to do? We're going to increase the temperature by this much here. Hopefully we can remember that the specific heat capacity is what we're talking about. So E is equal to mc delta theta over here. So the energy needed is going to be what? So let's go look at it. Energy will be equal to the mass. 4 grams must convert to kilograms. It will be 0.04. Yes, times by the specific heat capacity. 5200. Yes, specific capacity is from here. Times by the temperature change. We're going to increase it by this. So 50, 123, 123. Therefore, the energy is equal to 1.04 times by 10 to the power of 9. Okay. Oh, careful. I've got that wrong. Okay, just noticing that I've made an error in regards to the mass. Don't forget 4 grams is 0.004. Yes, it's only 4 grams over here. So I have to divide it by 1,000. So even I've made that error there. So there we go. Then we end up with the energy going to be 1.04 times by 10 to the power of 9 joules over here. Easy stuff. Okay, next one. 2.3. The idea of combining power from nuclear fusion was investigated using models. The models were tested before starting to build the first commercial nuclear fusion power station. Suggest why these models were tested. Why would you actually want to test models? Well, the main reason why you'd want to test the nuclear fusion beforehand is that, for me, there's multiple reasons if you check the mark scheme, but they accept answers in terms of to assess safety risks. So for me, I'd probably say to assess safety risks. Another reason why you want to do it is maybe to check if the process is possible, to ensure fusion is possible. Fusion is possible. These are all acceptable. There's a couple of other ones in the mark scheme I'll put down. So obviously there's 2 here. There's multiple things they can take. We can also say that to assess the environmental impact, to assess environmental impact, maybe to also say that to develop an understanding of the process, to develop an understanding of the process. Fantastic. Okay, so there's 4 reasons there, but obviously you can just pick 2. There's many more in the mark scheme for you to look at as well. Right, 2.4. Generating electricity using nuclear fusion will have fewer environmental impacts than generating electricity using fossil fuels. Explain one environmental effect of generating electricity using fossil fuels. Well, hopefully you can remember that when you're going to be obviously using the fossil fuels. This is a 2-mark question, so obviously it's going to be fossil fuels release CO2, release CO2, that's the main thing. CO2 can contribute to global warming, Okay, so that's those 2. You can also talk about sulfur dioxide being released, which can cause acid rain, or nitrogen oxides being released, which can cause breathing problems. They're also acceptable. Or you can also talk about acid rain, but check the mark scheme if you need extra support. Question 3. Student A investigated how the current in a resistor R at constant temperature varied with potential difference across the resistor. Student A recorded both positive and negative values of current. Figure 2 shows the circuit student A used. Describe a method that student A could use for the investigation. Right. So we're going to be looking at, so first of all, the student A recorded both positive and negative voltages of current. So you need to make the current positive and negative. Think about how you're going to do that. So we're going to be looking at how the voltage changes over here and this current changes over here. Describe a method that student A could use for the investigation. Right, so for 6 markers, they're usually graded in 3 levels, level 1, level 2, level 3. In this video, I'll be talking about how to get that level 3 and obviously get maximum marks out of 6. Well, first of all, the exam is looking for the method would lead to the production of valid outcomes. So the method that you choose will give me valid set of results. All the key steps are identified and logically sequenced. So all the key steps are identified and they're logically sequenced. So obviously when you're doing this, you must explain how you're going to get the results. You should explain that you need to get the current from the ammeter reading over here. You can measure the voltage of the resistor across R using the voltmeter. So let's put that down. So number 1, we're going to be record. So number 1, you have to say record current through R, the resistor R, using the ammeter. Yes. And number 2 is going to be to record voltage of R using the voltmeter. Good, the voltmeter. Right, that will only give you one set of results. So to have a range of results, so imagine your graph, you'd only get, let's say current and voltage, you'd only get one result here. You want a range of results. The only way you can do that is you need to be able to vary the current using the variable resistor. So this variable resistor, so 3, vary the current using variable resistor. And obviously that's how we're going to get the range of results over here, because you've now varied the current using the variable resistor, because that will change the current in the circuit. And then 4, it's going to be, so I think I've got quite a lot for the actual method right now, but I should also be talking about control variables and the risk assessment. So when you're doing this investigation, one of the main risks is that you can't let the current become too high. So we can also talk about ensure low currents are used over here, and then maybe 5, you want to get positive and negative values of the current. So how did I get these negative values of current? So okay, so the way to get the negative values of the current, I can swap the terminals of the battery here. So if I swap them over here, this one will look like, we can then get these ones over here. So by reversing the terminals of the supply, we'll get the range of values here. So so put that down here, reversing polarity of battery results in positive and negative voltages, positive and negative current readings. Easy stuff here. Another way, and you can also say that in between readings, you can just turn off the switch, yeah, to avoid it heating. So turn off circuit in between readings using the switch. Using switch. Okay, right, all right. So we've done a 6 marker over here. Look at that mark scheme correctly when you're doing it, and you'll be able to see that we've got all the content in here. But it must be a clean method, guys. And look, we've done basic steps that to take, and we've talked about some health and safety as well, because obviously that's going to be a valid method for us. Hopefully we can see that we've got a method over here, and then afterwards I'm talking about how I can get the negative values, and I've got some health and safety here, so everything has been included. Okay, let's start the next one. Student B repeated the investigation. During student B's investigation, the temperature of the resistance R increased. Okay, explain how the increased temperature of resistor R would have affected student B's results? Well, look, if the resistance of the resistor increases, what's going to happen to your graph? Well, if the resistance increases, the current will decrease. The current would not be directly proportional. So don't forget, previously in this one, because it's a fixed resistor, hopefully we can remember that it would be a directly proportional graph, yes? Because voltage is proportional to current because it's a fixed resistor over here. But now, because you're changing the resistance, current would not be directly proportional to the voltage, to the PD over here. And therefore, you can also talk about the line not being a straight line. So the line of the graph will not be straight. Will not be straight. Here we go. Excellent stuff. Right, now, okay, next one. Figure 3 shows that the scale on a moving coil ammeter at one time in this investigation. Okay, so that's the moving coil ammeter. So here, basically, this is the ammeter, just the dial here. What is the resolution of the moving coil ammeter? Right, the resolution is simply the smallest non-zero measurement. The smallest non-zero measurement. So look, the smallest non-zero, so this is 0, non-zero will be this one here. So this is 1, this will be 0.2. The smallest non-zero measurement is 0.2 amps. Easy stuff, yeah? Just make sure you can do that for most devices. It's simply the smallest non-zero measurement. Okay, so next one is going to be this. Student B replaced the moving coil ammeter with a digital ammeter. Figure 4 shows the reading on the digital ammeter. The digital ammeter has a higher resolution than the moving coil ammeter. Give one other reason why it would have been better to use the digital ammeter throughout this investigation. Okay, right, so the main thing is, look, this one's a digital one, and this one is going to be an analog one in which the needle is going to be moving. It's actually harder to read the needle over here, so it's going to be less chance of misreading, so we can put that down. Less chance of misreading. And then also, don't forget, because you have the needle, you can have that error of parallax error. So there's less chance of parallax error. Less chance of parallax error. There we go. Okay, so that's that one done as well. Question 4. A student investigated the density of different fruits. Table 1 shows the results. Fruit, the density over here. The student determined the volume of each fruit by using a displacement can and a measuring cylinder. What other piece of equipment would the student need to determine the density? Well, displacement can will give you the volume of it, and obviously to work at a density you need a set of scales. So yes, a top pan balance or a set of scales. So we accept a scales. Yes, scales. Yes, obviously to put your stuff on there. So scales on here. Okay, next one, 4.2. Write down the equation which relates density, P. So density is equal to mass divided by volume. Calculate the volume of the apple. Volume is equal to mass divided by the density. Moving that up, moving that down over here. So therefore, volume is equal to the mass, 85 grams. And look, because they've given me the mass in grams and the density in gram per centimeter cubed, I don't have to do any changes over here. So 85 is my mass divided by 0.68. So therefore over here it's going to be 85 divided by 0.68. It's going to be 125 centimeters cubed. 125 centimeters cubed. The student only measured the volume of each fruit once. The volume measurements cannot be used to show that the method to measure the volume gives precise readings. Why? So this question, it looks quite difficult, but it's basically asking you, do you understand what the word precise readings mean? Right, precise readings simply mean that all your results are close together. So the precise readings, give a reason why, it's because you can't show it's precise because in order to show they're precise, you need to have repeat readings for each fruit. For each fruit. And in order for them to be precise, they all need to be close together. That the readings are close together. That the readings are close together. That's the reason why, yes? So in order to demonstrate that you have precise readings, all your values, your readings, should be close together here. Because they've only measured the volume once, you can't do it. So you need to measure it multiple times, and all those readings need to be close together to tell you it's precise. Okay, next one. 5.1. During 1 year, 1.25 times by 10 to the power 18 joules of energy was transferred from the national grid. Number of seconds in 1 year is 3.16 times by 10 to the power 7. Calculate the mean energy transferred to the national grid each second. So how are we going to do this one? So if that is the total amount of energy that's transferred in 1 year, and that's how many seconds there are, the energy per second will be the total amount of energy divided by how many seconds there are. So the energy is going to be 1.25 times by 10 to the power of 18 divided by 3.16 times by 10 to the power 7. So over here, so it's 1.25 from 10 to the power of 18 divided by 3.16 times by 10 to the power 7. It's going to be the energy per second is 3.96 times by 10 to the power of 10. So it's going to be 3.96 times by 10 to the power of 10 over here. Next one, figure 5. Figure 5 shows a house with a solar power system. The solar cell generates electricity. When the electricity generated by the solar cell is not needed, the energy is stored in a large battery. Okay, energy stored in a large battery over here. The charge flows through the cable between the solar cells and the battery in 24 hours is 27,000 coulombs. Work out the mean current in the cable. Okay, right, so hopefully we can identify that current is equal to Q over T. The charge flowing is 27,000 divided by the time. 24 hours, how many seconds is that? 24 times by 60 times by 60 over here. So therefore, we're going to go for 27,000 divided by 24 times by 60 times by 60. I'm going to get 0.3125. Yes, amps. So we've done that. It's a relatively easy question for 4 marks, easy stuff. 5.3. At one time, the total power input to the solar cells was 7.8 kilowatts. The efficiency of the solar cell was 0.15. Calculate the useful power output of the solar cells. Hopefully we remember that efficiency is equal to useful power out divided by total power in. And then now you're going to rearrange it then. So the useful power out is going to rearrange it. So useful power out is equal to your efficiency times by total power in. So the efficiency 0.15 times by total power input 7800. Yes, I've converted that, so that's going to be 7,800 over here. So therefore it's going to be 0.15 times by 7800. It's going to be 1170. Yes, that's going to be my useful power output here. 5.4. It is unlikely that all the electricity that the UK needs can be generated by solar power systems. Why? Why do you think we can't do that? Because think about some reasons why. You need a large amount of area, so we require a large amount of surface area for this to occur. I accept that as an answer, and we also accept that the fact that the sunlight may have too low intensity, so sunlight intensity varies in the UK. Intensity may be too low. In the UK over here. Also they accept that due to a low useful power output of the cells, they're not that efficient. You can also talk about there's not that many hours of daylight in the United Kingdom. You also talk about there's a limited supply of the material needed to construct the solar cells as well. So you can also say that as well. Right, okay, figure 6 shows how the mass number and atomic number for the nuclei of 5 different atoms is shown. A, B, C, D, E. Okay, how many neutrons are there in the nucleus of A? Right, so nucleus A over here, how many neutrons are there? To work out the number of neutrons, you simply take the mass number and I subtract the atomic number. So obviously from here, for A, it's going to be 234 minus, and then the atomic number is going to be 86 for A, minus 86. So therefore it's going to be 148. That's going to be my answer here. Right, next question. Which 2 atoms are of the same element? Hopefully you can remember that to be the same element, you require the same number of protons, which is the atomic number is the same. So there's only one which has the same atomic number, so it's these two over here, D and E. So D and E over here, this one is correct as well. Scrolling down, it's going to be the following. Nucleus B decays by emitting an alpha particle. Draw an arrow on figure 7 to represent the alpha decay. So if it's going to emit alpha decay, hopefully remember that the mass number decreases by 4 and the atomic number decreases by 2. So the mass number drops down by 4, so it will drop down by 4, but also the atomic number drops down by 2, so it's going to be to there. So there, here we go. Yeah, happy with this. So there we go. So look, we've dropped from there to there. So that's my line. Yes. So a line between B and 86 protons, very good, and the same line between B and 22. So it's going from there to there. So this arrow going from there to there is important. Actually, to make sure I draw that correctly. So there, all the way across to there. That's my line over here. 6.4. What is meant by the random nature of radioactive decay? It simply means that it's unpredictable. You can't predict which atom will decay next. So it simply means that we are unable to predict which atom will decay next. Which atom will decay next? Will decay next. Decay next. Very good. So you can't predict which atom will decay next or when it will decay. So we'll put that in brackets, or when it will decay, or when it will decay. That's also acceptable here. So unable to predict which atom will decay next. I'm going to put that, sorry, my handwriting is really bad. So which atom will decay next or when it will decay as well. That's also fine as well. Next one, it's going to be 6.5. A polonium nucleus decays by emitting an alpha particle and forming a lead nucleus. There we go. The lead Pb nucleus then decays by emitting a beta particle and forms a bismuth nucleus. Okay, right, okay. Undergoes alpha decay, then that undergoes a beta decay, and that then undergoes a beta decay as well from there. Explain how these three decays result in a nucleus of the original element polonium. Right, how is it possible that we end up back at polonium? So if this occurs, then this occurs, then this occurs, how is that possible? Well, first of all, hopefully we remember that when alpha decay occurs, so initially at the start, 3 marks here, we know that the mass number, the atomic number decreases by 2. Yes, because it's alpha decay. Decreases by 2 as it is undergone alpha decay. But now it's undergone alpha decay. What happens when it undergoes beta decay? Hopefully you can remember that when beta decay occurs, the atomic number goes up by 1. So beta decay occurs twice. Beta decay then occurs twice. And every time beta decay occurs, the atomic number goes up by 1. So therefore, the atomic number increases. By 2. So obviously initially your atomic number decreased by 2 because of the alpha, but then one beta decay occurred, therefore you go up 1, then another beta decay occurred, you go back up again, and then you're left with the same proton number as you had initially. So therefore the proton number remains unchanged. Therefore the proton number is the same as the initial nucleus, the same as the initial value. Everyone happy that alpha decay, you've lost 2 for the atomic number. Beta decay once, you go up by 1. Beta decay again, you go up by 1 again. So you end up with the original that you had before. Because look, these two have the same atomic number. They have the same atomic number. Okay, next one then, question 7. A student investigated how the current in a series circuit varied with the resistance of a variable resistor. So how the current in a series circuit varied with the resistance of a variable resistor. Figure 6 shows the results. Okay, current and resistance over here. Right, next one's going to be this. The battery had an output of 230 milliwatts and the resistance of a variable resistor was 36 ohms. Determine the potential difference across the battery. Okay, this one's quite difficult. We need to use two equations to do this. So we're trying to find V. So we know that V is equal to I times by R. Right, we've got R, 36 ohms, but we don't have the current. But I can use this equation with regards to power to work it out. So we know that power is equal to I squared R over here. So therefore, we can work out the current. Current is equal to P divided by R square rooted. So the value of the power is going to be 230 times by 10 to the power of minus 3 divided by the resistance, 36, square rooted over here. So let's do that then. So 230 times 10 to the minus 3 divided by 36, square root the answer. I'm getting my current as going to be equal to 0.08, everyone. So my current is equal to 0.08 amps. And now look, I can use it over here. V is equal to 0.08 amps times by the resistance of 36. And therefore, this times by 36, my answer is going to be 2.88. That's going to be my value for the voltage here. So yes, two equations to work this out over here. Next one, 7.2. The student concluded the current in the circuit was inversely proportional to the resistance of the variable resistor. Explain how figure 9 shows that the student is correct. Okay, right. So what this means is that as the current increases, the resistance drops down. Is that true? So look carefully. If it's inversely proportional, that's true because we know that as the resistance goes up, the current drops down. But what this question is really asking you is about you've got to find the constant or proportionality between your results. Right, for this question, what they're really asking you is that you know that because they are directly proportional, there's a constant relating them. So if you were to take a current value times by the resistance value, you would get a constant. That will be true for any three pairs. So if I was you, I'd pick the pairs which are easiest to read off the graph. So I'll do it 3 times. So one of them, we could take this one. Let's say this is my first reading. I'll take another one which is easy to read off. This one I wouldn't take because it's midway. I'll go for this one, which is bang on. And this one again, which is bang on here. So for the first one, we'll just take the current value. So it's 0.2 times, so it's 0.24. Yes, times by the resistance value of this one is 12. Yes, that's the first reading. Let's do that for him. So 0.24 times by 12. I'm going to get 2.88. 2.88. That's my advice. The next one is going to be from here. We're going to go for the current value is 0.08. 0.08 is my current reading times by the resistance value of, there was a resistance value of 36 times by 36 is going to be, so 0.08 times by 36. I'm getting 2.88 again. Good, it's working out, guys. And then finally, we can see that's true. The last one, it's going to be the current value is 0.06. 0.06 times by the value of 48 times by 48. So 0.06 times by 48 is going to be equal to 2.88. And look, the constant is the same for all three of them. So we have shown that they are inversely proportional to each other. So we can just put that down. So the question is, so obviously all of that writing, you can actually just write that into here, over there. So we've got those values there. But we can also say that the current multiplied by the resistance is going to be equal to a constant. And when therefore that's going to be true. And also we've worked out that for 3 pairs of values, 2.88 is constant, is the constant for 3 values. For 3 pairs of values. Excellent stuff. Right, okay, next one. Let's go for 7.3. Figure 10 shows the circuit with a switch connected incorrectly. Figure 10, there we go. Explain how closing the switch would affect the current in the variable resistor. So when you close the switch, what will happen? Well, look, when you close the switch, first of all, what happens is that the current will simply not enter here. It will take the path of least resistance. So therefore, what will happen is the current will simply bypass that variable resistor and go this way. So what happens is the ammeter reading will drop to 0. Will drop to 0 as there is no current. As there is no current through the variable resistor. And the reason why is because the current will always take the path of least resistance. So current will take path of least resistance, will take path of least resistance. Yes, yeah, and the switch has zero resistance. As the switch has zero resistance, the switch has zero resistance. Excellent stuff. Okay, now scrolling down. Figure 11 shows a toy car in different positions on a racing track. Okay, so there's our toy car. It's going down here. The toy car and racing track can be modeled as a closed system. What does the word closed system mean? Closed system simply means there is no loss of energy elsewhere. So that means that the total energy of the racing track is constant. So this is going to be the correct one. Next one, let's go for 8.2. The car is released from rest at position A, accelerates due to gravity to position B. Okay, the mass of the car is this. The vertical height between A and B is this. Gravitational field strength is going to be that. Right, so first of all, we know that the car has gravitational potential energy, but as it falls down, it converts that gravitational potential energy into kinetic. So that energy gets converted into kinetic here. So what you're really trying to look at is that the GPE will be equal to the kinetic energy, yes? So the kinetic energy gained, so kinetic energy gained will be equal to the gravitational potential energy loss. Gravitational potential energy lost. Okay, right. So the gravitational potential energy at the start is mgh. The kinetic energy is going to be half mv squared. Okay, right, now look. The mass is the same on both, so g times by h is equal to a half v squared over here. There we go. G is over there, 9.8. H is going to be what? H is going to be the height. The height, what was that drop between A and B? The height is going to be 90 centimeters. Here, convert that to meters, 0.9. So therefore, 9.8 times by 0.9, and then I move the 2 up, so 2 times by all of that is equal to V, and then I square it the whole thing over here, over there. So obviously I move the 2 up over there, and then I take the square root, so 9.8 times by 0.9 times by 2, square root the answer, it's 4.2 meters per second. So 4.2 meters per second. Figure 11 is repeated below, so it's the same thing again. Okay, at position C, the car's gravitational potential energy is 0.2 joules greater than at position B. So the energy you have over here, GPE, will be 0.2 joules greater than at position B. How much kinetic energy does the car need at position B to complete one loop of the track? Okay, so how much do I need to complete one loop of the track? Right, okay, so logically, you need 0.2 joules to go up to the top. So you need this much energy to go to the top. So obviously, in order to make the full journey, you need greater than 0.2. Otherwise, you get to 0.2 and you're stuck there. You want it to keep going, so you need to have more energy than 0.2 joules in order for you to complete the journey. Otherwise, you just go to the top and you stay there. But you want it to complete the loop, that's why you keep going. Okay, the reason why is because you need the car to be moving at C. So car needs to be moving at C, yes? At C to complete the loop. Very good. Okay, so next one, let's go for 9. So 9, a teacher demonstrated that the relationship between the pressure in a gas and the volume of a gas. This is the method used. Record the initial volume of the gas in a syringe and the pressure reading before any weights are attached. Add 2 Newton weight to the syringe. Record the volume of the gas and the reading on the pressure gauge. Repeat from steps 2 to 3 until a weight of 12 newtons is attached to the syringe. What was the range of the force used? So the range is obviously going to be the range of weights that you're going to be using. So you can accept from here, you're going from 0 to 12 newtons. But the mark scheme also identifies that obviously you start off with 2. They also accept that you can go from 2 to 12. So they give you marks for this one or this one as well. Yeah. So 0 to 12 or 2 to 12 here. Give one control variable in this investigation. One control variable in this investigation What must you keep constant in this case here? What must you keep constant? Okay, so one thing you must keep constant in this investigation is going to be the temperature of the gas. If you change the temperature, the pressure will change. So we're going to keep the temperature of gas temperature of gas must be kept constant. Or you could also say that the mass of the gas itself, so the total mass of the gas as well, you can also argue. Right, next one, let's go for when the volume of the gas in the syringe is 45 centimeters cubed, the pressure gauge showed a value of 60 kPa. Calculate the pressure in the gas when the volume of the gas in the syringe is 40 centimeters. Right, hopefully you remember that P1 times by V1 is equal to P2 times by V2. So pressure 1 is going to be 60 kPa times by 45 will be equal to the pressure on the second one, we don't know, P2 times by 40 over here. Therefore 60 times by 45 divided by 40 is equal to P2. So therefore from here 60 times by 45 divided by 40, I'm going to get 67.5 kPa. 9.4, when the volume of the gas is increased, the pressure on the sides of the walls decreased. Explain why. Explain the reason why. Well, if you make the volume bigger, what's going to happen to the number of collisions of the particles per second? So as volume increases, we know that there are less particles colliding with the walls per second. There are less particles colliding with the wall per second. Yes, per second. That's going to be the main thing. There's less particles colliding with the wall per second, and therefore that means that there's a less of a force, so therefore there's less force acting. And if there's less force acting, guys, so there's less force on the walls of the container, and therefore there's less pressure, as pressure equals force over area, as pressure is force per unit area. Over here. And last of all, question 10. Figure 10 shows some overhead power cables in the national grid. Explain the advantage of transmitting electricity at a very high potential difference. At a very high potential difference, the current is low. So at high PD, current is low. So high potential difference therefore means low current, And if there's low current, there's less of a heating effect in the wire. So there's less, so therefore there's less energy lost as heat. Less energy lost as heat. And obviously therefore, which means that it's going to be more efficient. So it's more efficient because now you can transfer more energy. So it's more efficient now. 10.2. It is dangerous for a person to fly a kite near an overhead power cable. Figure 14 shows a person flying a kite. The person could receive a fatal electric shock if the kite was very close but not touching the power cable. Explain the reason why. Why is that possible? It's because obviously, because let's just say the power cable is here. What happens is there's an electric field around the power cable. So the reason why is because there's an electric field around the power cable. So there is an electric field around the power cable. So what can happen is that because there's air in between, what can happen is that charge can travel through the air into the charge over here. So the key thing is going to be the air can conduct the charge, and then obviously it's going to be last of all to the person. There we go. So you can accept that answer here. So there's an electric field around the power cable, and obviously because the air will act like a conductor, that charge will then pass through the air and then strike the child here. Okay, next one. A scientist investigated how the potential difference needed for air to conduct charge varies with distance between a cable and the earth. Figure 15 shows the results. The data in figure 15 shows the relationship between potential difference and distance when the air is dry. When the humidity of air increases, the air becomes a better conductor of electricity. Draw a line showing the potential difference changes with distance if the humidity of the air increases. Alright, so what this means, this question means that as the humidity of the air increases, what happens is that it's a better conductor of electricity. So therefore the charge can't build up. Yeah, so if the air becomes a better conductor, the charge can't build up. That's the key thing. So what happens is, yes, the potential difference increases, but it will never build up to the same amount. So it will be lower than before. So the potential difference does increase, but it's less than before. Because obviously the air is a better conductor. So there can't be a large potential difference here. Okay, next one. So 10.4. Figure 16 shows a cross-section through a power cable. A 1 meter length of single aluminium wire is a better conductor than 1 meter length of steel wire. The individual wires behave as if they are resistors connected in parallel. Explain how the current in a steel wire is different to the current in a single aluminium wire. Right, so initially this is kind of difficult to get our head around, but they have the same voltage. So let's say you were to connect them up. So let's say we have a battery over here. They would have the same voltage across all of them. So there's the same voltage across all, yes, across all of them, yes, all wires. But the key thing is this: because there's 1, 2, 3, 4, 5, 6, there's 6 aluminium and they're in parallel. That's the same as having 6 aluminium wires. 1, 2, 3, 4, 5, 6 of them in parallel. Yes, so 6 of them are in parallel. This is the aluminium one over here, which is obviously it's easy to pass through when they're connected in parallel. So what happens is that the resistance of the aluminium ones is less than the steel. And by converse statement, you can say that the steel has a greater resistance than the aluminium. So therefore, you can say that the steel has greater resistance than aluminium. And obviously, if it has greater resistance, it therefore has less current. And therefore, less current. Therefore, less current. Therefore, less current. Okay, now scrolling down is going to be question 11. A student investigated how the temperature of a lump of ice varied as the ice was heated. The student recorded temperature until the ice melted and then the water produced boiled. The specific heat capacity of ice is less than the specific heat capacity of water. How do we know this? Okay, so first of all, when you're looking at this graph, this is a solid, this is a liquid, and this is the gas state. So we can see that the gradient of this line is steeper than this one over here. We can see that obviously this one can heat up in a shorter amount of time. So therefore, explain how figure 17 shows this. The gradient is steeper for ice than water. Good, so the gradient of the light tells you, because if the gradient is higher, it can easily heat itself up. And therefore, it means it has a lower specific heat capacity. And which means that less energy is required to increase its temperature. So therefore, less energy required to increase temperature. Okay, next one is going to be figure 11.2. The specific latent heat of fusion of ice is less than the specific latent heat of vaporization. Explain how figure 17 shows this. So, is the specific latent heat of fusion of ice less than specific latent heat of fusion vaporization of water? So the fusion one is here, yes, compared to this one over here. And look, you can see this because the length of the line here, this length of the line tells you how much energy you needed. So it spent a longer amount of time changing state to go from a liquid to a gas. So we can see this by that it would took a longer amount of time for it to vaporize. So we can say that the water took a longer amount of time, to vaporize. Good, to vaporize. Yes. Therefore, it took more energy to go from liquid to gas, than solid to liquid. Everyone, yes? So liquid to gas, then solid to liquid. So if you look over here, look guys, it took longer. So that's therefore we needed more energy for you to be able to change its state. Okay, right, next one. 11.3. A second student did the same investigation and recorded the temperature until the water produced boiled. In the second student's investigation, more thermal energy was transferred to the surroundings. Describe 2 ways in which the results of the experiment in 17 would have been different. So obviously, if you're transferring more energy to the surroundings, what's going to happen to all of these? Well, if you are losing energy in terms of heat, what would happen is obviously it would take you longer to heat it up. So initially, it would take you therefore it would take you longer to heat it up, then longer to change state, then longer again for you to heat up again, and then even longer to change state again. So what would happen is that the gradients of the line will become less steep. The gradients of the line become less steep, and the length of time when changing state will be longer as well. So look, the gradients will be less steep, and the length of time changing state would be longer as well. So number 1, gradients of lines will be less steep for the ice and water, and then also it would take a longer amount of time. So the horizontal lines, don't forget, the horizontal lines will be longer as well, obviously, because it's going to take you a longer amount of time for you to change the states. Okay, right, so it will be longer as more energy required to change state. Easy stuff here. Okay, last one now. So last one. Okay, when the water was boiling, 0.03 kilograms of water turned into steam. The energy transferred to the water was 69 kilojoules. So when it was boiling, that's how much water turned into steam. The energy we transferred to the water was 69 kilojoules here. So now we're just going to try and rearrange it. So energy is equal to mass times by the latent heat of vaporization. Therefore, latent heat of vaporization is equal to energy divided by the mass. The energy was going to be 69,000 divided by the mass, 0.03. So it's going to be over here, 69000 divided by 0.03. I'm getting the value of 2300123, and the units, because you're dividing joules, which is energy, divided by kilogram, it is joule per kilogram over here. Easy stuff. Okay, so we're done for this lesson, and obviously it's a long video, so take your time when you're actually going through this. Make sure you look at this paper and the mark scheme yourself, and hopefully now I've gone through it, it makes a bit more sense to you. Okay, we'll leave it for today, and make sure you hit the like and subscribe button to get my channel going, and good luck in your studies. Ciao, ciao, and goodbye.